if I was going to state the possible zeros for this one, if I state the possible zeros, I'm looking at plus or minus all my factors of 63. So it's 1, 63, 3, 12, 7, and 9. And then what are leading term coefficients? No, it's not 12. It's 21. I was reading it backwards. And then what were the first? It would all be divided by then by 1. That would be state the possibles. Now, here's the nice thing. It kind of cancels itself through when you see the plus minus on the top one because it works itself out. Now, here's the deal. When you have to find your zeros, when we did this in class, what didn't you have? What do you have? Yes. Yeah, state the possible zeros would be something like that. Now, here's the deal. If it is to find all possible zeros, now you could go through synthetic division all day long and look for them, but wouldn't it be quicker to start the problem? I don't have my calculator with me. It's not a bad idea to think that, but remember, you only have so much time. No. So if I'm writing this one out, x to the 5th and if I go right to my table, thank you. If I go right to my table, I know that I can find a 0 to start with. In this example here, it gives me a 0 at -3. Okay? So if I have a 0 at -3, that means I'm going to start my synthetic at -3 because as you go back and you're looking at the graph, if I look at the graph of this, it looks like I'm getting some funky numbers, some funky fractions in there. I do. But here's the thing, as you get into this, using the calculator to help you find an initial 0 is great, because then you'd have to use some other means to get you going. So I'm using the 0 to start. If I use -3, let's see, 1, 3, 4, 12, -21, -63. 1, -3, 0, 0, 4, -12, 0, 0, -21, 63, 0. Okay. That gets me to a degree less. So I have a 0 at -3, so my term, x plus 3. This becomes x to the 4th plus 4x squared minus 21. And I can factor that via the same way I would any other trinomial. And that's how I'm going to be able to find those other weird zeros. So what times what's -21 that you add together to get positive 4? Let me slide this up here. So I'm going to get x squared plus 7, x squared minus 3. Now, way up here, I had my 0, or my term here. Now, from those, I can write out my zeros. I could say I have a 0, let me know, at -3, plus or minus the square root of 3. Where's this one at? There you go. Plus or minus I root 7. So even though you have the calculator is going to allow you to start the problem You just still have to be able to figure out how to finish it. Does that make sense? So that's a good example of what the calculator will be able to help you out with. Yes, sir. I suppose. Are you on the ID 1 or ID 2? You said 43? Okay. That's gross. All right. So in this one here, you have to figure out what times what's. What is 27 times 8? 260. So now it's nice that it works out cleanly here, because when you factor that, what times what's 216 that you add together to get 217? I know, 216 and 1. It's nice when it works out, okay? So we put that together, we have 27x to the 6 plus 216x cubed plus 1x cubed plus 8. Ugh. So now we have to figure out, well, does 27 go into 216? It does. How many times? 8? Yeah. Well, this so happens now is that you've got two sets of perfect cubes. The cube root of 27, x cubed, would be 3x. Okay, so we have the special patterns to follow for that. Versus you stupid pattern. So, let's see. We get 3x plus 1, 9x squared minus 3x plus 1, I believe. And then this will be x plus 2, x squared minus 4, or minus 2x. I believe that's the pattern, if I'm not mistaken. The difference in cube because it's x minus b. It's not double in the second term, is it? No. Oh, it's 4. Yes, it's got to be a 4. Yeah, that part's the 4. I was thinking about. For some reason, I thought about the middle one. I forgot about that one. Ooh, that was fun. That's a weird shirt. It's got buttons. On the other side. Others. Because, you know, my sleeves get unrolled so easily. I'm Mr. Fashion. All right, does that help on that one? What else am I looking at? Where's bum rush this? This is good times. We get going. Simplifying, multiplying. Sure. 41. Okay. Now, here's what I would do. To alleviate making a bad mistake here, I would put that in my y equals. and then look at the table. You know what I mean? By doing that, then I know I'm not going to screw up an add or a subtract type of thing. That's the easiest way to do ones like that. Otherwise, what do we have here? I'm going to evaluate -4, so it'll be -4, -3, -8, 13, -14, 4. Get 12? No, that's just a synthetic substitution. Yes. Does that help? What do we got? Write the polynomial function of the least degree polynomial least degree. Yeah, you work backwards on these. Now, and especially if you have a calculator, you can kind of fudge your way through most of it. So if I wanted to figure out what's going on with this one, I know that I have x-intercept would be at 2. My x-intercept would be at 2. By 2, add 8 divided by 4. Okay. Pay attention to what we're doing. It'd be helpful. The vertical asymptotes, see our term be x minus 3, x plus 2. So I have vertical asymptotes at 3 and -2. I have a y-intercept at -8 over -6. So that's what, 4/3? The y-intercept is when all your values of x are equal to 0. Bless you. It's not one that we always found a lot, but I found that by knowing what that is on a graph, sometimes it's helpful to sketch something. So we have x-intercept, vertical asymptote, y-intercept. Now we think about horizontal. Horizontal asymptote in this case, I believe, is at 0 because the degree of the numerator is 1 less than is smaller than the denominator. So your horizontal asymptote. Okay, here you go for that. And obviously, if you're looking at a graph, if you put that in your calculator, you could probably fudge your way through that. Because you have a calculator. It has a button that says y equals. Yes, ma'am. Yeah. Yep. You all right? Worry about it. Let's see. What didn't we really look at a lot of? Conics. Yeah, remember we're talking about conics. Like I said before, I'll give you guys that sheet that has the app, what the pictures of the apps look like, just like you had on the test and stuff on conics. When you're dealing with conics, remember what things mean. No matter what, when you're working with a conic, let's see, I think I had a conic sheet on here somewhere. I wanted to, that's this one. Let's say I want to do one of these. Use the information to write the standard form of a hyperbola. That aren't multiple choice? Yeah, there could be, absolutely. Because these types of problems are ones that it takes a minute to work itself through. So even if it was multiple choice, you still had to work it through. So that's why I thought these are fairly decent ones to have until you get a point for trying to have it. This isn't on there. This is from that conic review. Now, in this one here, excuse me, if I want to write the equation, and they told you that's going to be a hyperbola, it just had to get cut out. What we have to do is decide what direction is the hyperbola going. Is it going up and down, or is it going left and right? So by doing this, we do a quick little rough sketch. So 8 and 11. So if my vertices are there, that means that it has to be an up and down hyperbola. Has to be. Now, here's what happens. We know now that the x value of the, or the h value, I should say, for this hyperbola is going to be at 8. Okay. The y value will be at the halfway point of 11 and 5. So what's 11 plus 5? And what's half of that? 8. So your center is now at 8 and 8. Now, you can, that's the other thing. You could probably figure out what's being added to it. So, excuse me, as we get back to the calculator here, when I'm looking at the hyperbola, let's throw this in here real quick. So I know then I'm looking at a y squared. I have a center at 8 and 8. Now, if I'm at 8, 11, 10, 8, the distance from the center to vertex is always your what? A value. So your A is 3. The center to focus. Well, the focus, notice, it's adding and subtracting root 109, which means your C value is root 109. Okay. So when you're looking at the hyperbola, if I know I have A is 3, what's A squared? If C is root 109, C squared would be 109. Which means B squared has to be how much? 100. B squared has to be 100 because A squared plus B squared has to equal to C squared. So you don't have to overly math it all, you just have to know how do you get to it. So we wind up with y minus 8 quantity squared over 9 minus x minus 8 quantity squared over 100 is 1. Okay. It's the idea of knowing what does the A value stand for, what does the B, bless you, what does the B value stand for, bless you, what does the C value stand for, what is the directrix in terms of the focus, or not, yeah, things like that. Remember, the directrix is the line opposite going the other direction. It's the P value going through those. Bless you. Okay. Speaking of boogers and snots, make sure you have your own Kleenex marks. I don't have any. I've never had any, so I won't have any. Is everybody sneezy? It's, I'm still sneezing a lot, but I'm not dead. Finally, it took me a weekend where everybody was not dead. What else we got? We got 10 minutes left. What else? Yes, ma'am. 38, ID1, ID2. Find the roots. So, remember the trick. The trick for one like this is that once you see 4 terms, automatically see if you can group it. So if I go this route via grouping, I take out an x to the 4th, I get 3x squared plus 5. Take out a negative 1, I have 3x squared plus 5. So now I have x to the 4th minus 1, 3x squared plus 5, which means I can break down that x to the 4th minus 1, because x to the 4th minus 1 is a difference of squares. That gives me x squared minus 1, x squared plus 1, 3x squared plus 5. If it's find all roots at this point, you can go ahead and probably just set all those terms equal to 0, because those are pretty quick to work with. It's just that 3 and the 5, you have to think the square root's going to become crappy. So we have real roots at plus or minus 1, imaginary roots at plus or minus I. Here it's going to be x equals I, that's going to be the square root of 5 over the square root of 3. So that becomes what? Plus or minus I root 15 over 3. So you have 2 real roots, 4 imaginary roots. Does that make sense? Plus or minus, add 1, take the square root. X squared minus 1, remember that's just a difference of squares, x plus 1, x minus 1. Okay. Which one? Divide. Woo, long division. I don't know if it is or if it is not, because if it's written out like this, if I divide it, see what happens. Now, that gives you a remainder of 3. So if it said divide using long division, then I would have done it differently. Because this one just says divide. That's divide, but then here's what you wind up with. You get 5x squared plus 10x plus 8 plus 3 over x minus 5. Because that value of 3 is your remainder.
Does it work like that? That's so much easier.
The only thing that, here's the problem though. If this was a 2x minus 3, you can't do it then, because you can only synthetically divide when you have a complete if it's got a singular 0 like that. But you can do it with a fraction, but not with that. Because then you'd have to, then you would have to literally do that long division. But as you guys saw, long division isn't that difficult. Yes, Ellen, what do you got?
So that
Dance, dance, dance. Dance, dance, dance. 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 Like that little Dr. Pepper dude. I feel young, the Dr. Pepper dance. Ooh. All you have to do, hey guys, we're talking about the dance moves or end behavior. Arrows, dance moves. All you need. F of X and X and all that other junk, whatever. Dance moves. Yeah, if they're written like if it is possible to have that, but remember what that if it does write out like that. If you're looking at end behavior of something that's like x cubed plus 2x minus 4, you guys all agree that it's going to do this and this. So the way that it would be written as x approaches positive infinity, f of x approaches positive infinity. It's the same idea. As x gets larger, y gets larger. As x gets smaller, y gets smaller. That's all it means. Dance, 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 dance.
You want to write it like that?
Dance. What else we got? I hope not. 48? Find the zeros we go. Find the zeros we go. There you go. I'm going to start the problem like this. So it's 5x to the 4th. 5x to the 4th, then what? Negative 48x squared. Okay, so right away, I don't want to factor all that because that looks hard, but I know I have zeros at plus or minus 3. So I'm going to use synthetic division with plus or minus 3 and see what happens. So you see I have to put zeros in. I do that again with the negative 3 because I know it works. So I went from x to the 4th, x cubed, x squared. And then that's how you get your last set of zeros. So it would be plus or minus. Oh, same thing with that 3 over 5, the square root of 3/5. So you have zeros at 3, negative 3, and this would be at plus or minus square root of 3/5, so it would be negative 15 over 5. I'm sorry, I meant sorry. The plus or minus the square root of 15 over 5. When you have something you're not sure how to start on, use a calculator, find a 0, and then it opens up the problem. See what I'm saying? This is kind of the reason why, when you get into most of this, why I don't let you use a calculator, because it does too much. Silly calculator, Alliance. That's fine. It's fine. No problem. And I'll be here in the morning. Probably at about 7:30. You're like, yeah. I might have Lofthouse start the final for me. That way I can deal with you beforehand. Walking in. Don't stay up on it, guys. Don't stay up all night looking at this stuff. Seriously. I literally just go over a few things here and there, review how to set up, work with accounting stuff. Yeah, this was 3/5. So when you take the root of that, you have to bring up the root. Are you helping now? They're a much better teacher than I am. Much nicer people. You can use your sleeve.